So just in case, if there's someone who didn't get my message, I'm sharing again the link to the video, very short video, which explains how to install Dezyne. So is there any person here that doesn't have the Dezyne setup? If no, I think we can start. So good morning, good afternoon, my name is Karol Kobiela, and I'm working in the Verum Dezyne. I'm working on the Verum Dezyne product, and together with Rutger and Paul, that's also here, we are going to show you the brief explanation of what stands after design. And I also will try to show you a short example, then interactive example, where we try to implement the system controller for the driveline assistant, pretty common in the modern cars. So first, there will be really short theoretical introduction. Okay, can you see my slides?
Yes.
Okay, so let's start with the importance of the software correctness. Nowadays, we can observe that there's rapid increase of the complexity of different software applications. And for example, the washing machine that has software that weighs more than 1 megabyte is not something unusual. We have a lot of new communication protocols. We have far and more advanced transportation systems. And also because we are trying to cut the costs as much as possible, we are robotizing and automating our industry. Because of that, there's plenty of bugs and defects that were introduced, and the current techniques that we're using may not be enough to actually solve that problem. And the defects can be fatal and extremely costly. Safety critical systems is something quite obvious, but we also have subject of mass production. And for example, once time the Philips has problems with their TV remotes, and the infrared protocol that it was using had some problem. And they actually had to recall 1 million of the remotes. So even with the very simple applications that are mass produced, may cause a huge cost problems for the company. What is the system verification? So first of all, I want to describe what is the verification. And verification is to check whether a system fulfills the quality requirements. So by the quality, it means all the typical bugs we can encounter, all the race conditions, all the logical problems, all the quality issues with the code. And just to make sure, the verification is not validation. Verification is, are we building the thing in the right way? So are we coding our program in the correct way, and it's passing all the quality standards? And the validation is more about the requirements. So it answered the question: are we building the right thing? We have different software verification techniques. The most popular are the peer review. So we have the manual code inspection. And with this number, so 31 and 93% of defects that being found, we can say that these techniques are pretty weak against the concurrency systems and advanced algorithms, where we have multiple states, multiple scenarios that can happen, and it's really hard to predict just by reading the code. Another popular techniques are the tests. So we are manually creating some test cases together with the test input sets, and we are trying to predict all possible scenarios that could happen. But eventually, there is no sufficient amount of tests at the end, and there's always that little small case that we actually could omit. As a result, the testing consumes up to 50% of the project cost, and typically it takes more time than the actual development. In the late 90s, Microsoft said that accepted defect density is 1 defect per 1,000 lines of code, because basically there's no sense to spend so much time and cost just to find all those minor bugs. So they just accepted the maximum amount of the bugs. This is the bug cost over time. So the continuous line is the is the defects introduced at the different project stages. So we have the analysis, we have the programming, the system testing, and the dotted one is the amount of defects that are detected. So as you can see, typically we are finding most of the problems at the system testing, and the real issue is that the cause of such error goes really up in the next stages of the project. So our goal is to move this dotted slope maximum to the left. So we want to find all the possible defects as early on the project stages as possible. And here, that's why I want to introduce the formal methods. And the formal methods are actually applied mathematics from modeling and analyzing the informative and communication technology systems. So basically, we want to introduce the advanced math to actually prove that our code is correct. And the basic advantages is the early verification, basically from the first steps of the design process, more effective verification techniques, and higher coverage of the system. Also, at the end, we also want to reduce the verification time by using some automated tests. Current usage is, of course, the safety critical systems. We have all the safety standards for the aviation, for the automotive, and the industrial functional safety standards. And as you can see, those are highly recommended by FAA, IEC, and NASA. So pretty advanced high-tech stuff. Next up is the model checking. So model checking is the one of the methods called as a formal verification. And basically, model checking is the method that design is using under the hood. And what it is basically a system model and specification. Well, the idea is that our system model and our specification can be represented in precise mathematical language. So we can just translate our lines of code into some kind of mathematical expression. And by specification, we mean some kind of correctness property or criteria. And by criteria, I mean the properties like deadlock, live lock detection. So all the logical jumps we can suffer from, race conditions, dead code, unhanded exceptions, interrupts, illegal states, non-compliance, and out of range fix. So those are pretty much the most common errors and bugs we can find in our code. And what we are doing, we are trying to express them as a logical task. This method is applicable for the system that can be represented as a finite state machine. So I will explain what the state machine is, but basically, if you are familiar with the enums in the C, or you are familiar with the SysML, or you are familiar with the state flow from the MATLAB, you probably know what is the state machine. But in general, the system our software can has different states, and we can move through those states through some kind of events and triggers. And the idea of the model checking is to use our properties expressed as a logical task to check each property, well, each specific part of our system, if it met the property, well, if it met the property task. So I can compare it to the mathematical task exercises we had in the secondary school, where the teacher was asking, prove that a to the power of 2 plus b to the power of 2 means that a is equal to 2 times b. So typical proving task. Last thing is that the model checking tools needs to deal with the combinatorial blowup problem, because as you can imagine, when we have the complex systems, we can have dozens of states that the system could actually find in. And the idea is to deal with the situation and only check all the relevant states that we are actually going to use. Any questions so far? So summarizing, we just want to use math to prove that our code is correctly. Some example applications. So Microsoft is using it for verifying their own driver controllers, because they found that 85% of the system crash are caused by the external supplies drivers. So they've made a tool called SLAM that actually checks the compliance of the Windows API with the external drivers. Also, the famous dam on the Rotterdam, which basically closes the entire port when it's being closed. It's also being controlled clearly by the software, and the model checking was used to verify if the software is correct, because every false alarm can cause huge cost problems for the port. Recently, we have Amazon, Facebook, Tesla, NASA. They're using it for the cybersecurity, for the autopilots, for the space operations, etc. Just to remind, what is the state machine? So basically, state is it's a state when the system actually can get into, and it can change the state depending on what is happening. So we have really simple vending machine when we are starting our interaction with. It's in the pay state. When we are going to insert the coin, it is moving to select, and we can either choose, let's say, click soda or click beer. It's getting to the dispenser mode and goes back to the pay. Any questions about the state machine? Is it familiar to all of you? If not, I will continue. So this is like simple graph of how the model checking looks like. So as I mentioned before, we have the requirements, which are the properties, which are all the quality criteria we have listed about the deadlocks, non-deterministic, etc. And we have our system. So this is the actual our algorithm, our code that we want to use. So what we're doing, we want to formalize the requirements. So we want to express them as a logical task in our formal language. And same for the system, we want to express it as a system model, which is being translated into formal language. And then we have our model checking tools. So together with the formal language, we're getting the tools that are able to exercise our system model with the properties we have specified. And those properties can be either satisfied or violated. And the nice things about the model checking is that it allows you to simulate your system. And in case if there is some problem with the violated property, we're getting the location error, which means all the steps to reproduce the error. The disadvantage of this approach is that you need to make sure that your model and your properties are correct, because if you are going to wrongly translate your system to the formal language, basically means that your model checking is a trash. So you need to basically learn how the formal language looks like and make sure that the translation from your target code to the formal language is correct. Otherwise, it's a trash. You cannot actually effectively check your algorithm in terms of bugs. So about the model checking, about the formal languages, we have the MCRL2, we have the SPIN, we have new SMV, and for the design, we are going to use MCRL2. And nice thing is that the design is an intermediate language that basically covers all the nasty things, all the math underneath the syntax that is similar to the C or Java. So it's a convenient bridge which allows you to very smoothly move between the formal language, so the formal verification, and your target source code. So we have our domain-specific language. We directly translate into the formal language. And then if we are saying that our code is verified, we can just directly generate the target code, the C, C++, the C#, that is completely deployable and ready to be used. The only thing that needs to be noted is that we are using the design by contract approach. So basically, it means that we need to specify our interfaces. We need to specify what we expect from between each models and what kind of return value we want to actually receive. If you are familiar with this SML, there are plenty of concepts that you are familiar with. So we have the interface and the components. And at the end, as I said before, we have the included target code generator. So any questions at this point? Okay, so moving on. Okay, so we are basically done with the theoretical explanation, and now I just want to show you a really short promo video for the Volkswagen Driveline Assist. This will be our base for the project. Okay, it takes 2 minutes. Oh. Yeah, I can see there's no audio. Just like mentioned. Okay, let me just fix that. Okay, now it should work fine.
The Travel Assist feature in your Volkswagen combines adaptive cruise control with lane assist for added driver assistance, while emergency assist can recognize driver inactivity and help control the vehicle. When activated, Travel Assist independently controls the accelerator, brake, and steering to help maintain a distance from a vehicle ahead and stay within the lane. To activate, ensure that adaptive cruise control is selected. With a set speed above 20 miles per hour engaged, press the Travel Assist button. A green indicator light turns on in the instrument cluster display. If the lane markings are green, the system recognizes both lanes and is ready to assist. Travel Assist helps maintain a relative position from vehicles in front while helping to hold the vehicle within marked lanes. If the driver applies the brakes, Travel Assist is deactivated. To reactivate, accelerate to the desired speed, then press the Travel Assist button again. If no contact with the steering wheel is detected after a few seconds, a message will display instructing to regain steering control. If contact is not restored, an audible warning will sound. The display warning will turn red, and a brief braking intervention will activate. If no driver activity is detected, emergency assist will engage, helping keep the vehicle in its lane and, if necessary, slowing the vehicle to a full stop, applying the parking brake, and activating the emergency flashers. Control can be regained at any time by moving the steering wheel or pressing the accelerator or brake pedal.
Okay. So for this workshops, I want to implement a simple controller for the line assist system, which we decide either we want to enable or disable the system. And let's try to specify some requirements for this solution. One problem with some cameras. Okay. So we want to make a system that provides a feedback to the driver about the system being enabled or disabled. So that was the green dot that the driver was seeing. We want to activate only when the minimum speed is reached. And we want to deactivate when the no steering wheel contact detected for a specific time. Well, in the video, we saw that it's about braking, but for now, let's just make a placeholder that will just deactivate the system, and eventually it will do something more if we implement those nice to haves. Whenever the steering wheel contact is resumed, we want to cancel the timer, and we want to deactivate the system when braking is applied. Any questions so far? Okay, if not, let's just move on. So this is like proposed structure of the system we want to use. So as you can see, we have like distinction between the components, which are those blocks, and we have also those yellow black arrows, which mean the interfaces. So the way how we contact between the components. So we have the steering wheel that will tell us if the system was enabled or disabled by pressing the button, and also it will tell us do we have or we don't have the contact with the driver. For the car state, we assume that we want to check what is the car speed to evaluate if you're able to enable the system. And the braking system should get the information from us in case we want to emergency brake because we don't have the driver control for a specific amount of time. Also, we have connection to the external system, to the utilities that also we're going to use, like timer. Okay, that's all from the theoretical part, and we can just jump into the coding. So right now, I would ask you to open the VS Code and create a new file with the Dezyne extension at the end. So just a simple new file, the Dezyne, and it should open. Okay. And let me know when you are ready. Okay, so all of you actually was able to open the VS Code and have this console? If not, let me know. Okay, so let's start the code. I listed all the requirements we saw. And for the beginning, we can actually start with creating our main component, which is the line assist control, let's say. So the component, this is one of the two main blocks we're going to use. The other one is the interface. So I will try to make it a little bit bigger. Okay. And we want to use interface to communicate with our steering wheel. So you can say we have our provide, which means that implements the interface. And we have, if you are familiar with the object-oriented programming of the system, you probably know what is happening right now. Okay. And this is our interface. So this is all the communication that our component is going to speak with. And also the component specifies the behavior. So what we're going to do with all the events and triggers we're going to receive through the interfaces. So to start, we actually need to communicate with our steering wheel. So let's make another base component we're going to use in design, which is the interface. So the keyword interface, and we want to specify our steering wheel interface. So the interface is actually has a guarding role in the design. It specifies what kind of inputs we can expect from the upper components. It has a state, and it decides, depending on the state, what kind of signals we want to pass to the component and what kind of return values we want to expect. So let's now say we want to get from the driver the information about the line assist button being pressed. So let's say we have the line assist button, where the in means that this is the signal that is going into the component. And also we need to give it a type of return. So just like in the C or Java, we want to say that this is the Boolean value, because we said in the requirements that we want to provide the feedback to the driver about the system being enabled and disabled. So our component will return the true value is it's able to enable the system, and false if it's not able to enable the system because, let's say, the speed is too low. Now, when we have our inputs, we want to specify also the state of the interface. So we already want to know is the state can be enabled or disabled, and to do this, we can just specify the enum. So again, just like in the C in the Java, we can make disabled and enabled states, and then we can specify behavior of our interface. So we expect that when the car starts, our interface, our line assist controllers, will be always disabled. So this is our variable which holds the state of the system, and we can say that our state is disabled. Okay, so this is our initial conditions for the system. And because we have state, we want to describe the state guards for the system. So we want to describe how the interface should behave when the system is enabled or disabled. So we have our guard clauses, and we want to say that in the enabled, we have something happening. And in the disabled, we also want to describe the behavior of the interface. So far, so good. Any questions from you? Okay, if not, let's go ahead. And right now, when we are in the enabled, we want to describe what will happen when the line assist button arrives. So there's a keyword on, and we want to list our trigger. And now we want to describe the behavior of the interface when we have the button enabled. And in this situation, we just want to change our, okay. we want to change our state to the enabled. Okay. And also because we described that we want to give the feedback to the steering wheel, we also need to reply with the true value, which means because we have changed the state to the enabled, we want to reply to the steering wheel that, okay, fine, we have changed the mode. Same thing we can do for the disabled, but this time we just want to change the role, so this will be disabled. Okay, so far so good. And we are done with the interface. Now we can actually implement it in our component. But just before, we can actually already start to verify our system. So by clicking the right click in the context menu and getting the verify file, we are actually translating our interface into the formal language, and we are doing the formal verification of the system. Okay, we have some problems with the code. It already shows that we have some dead code that will be never executed. And where it actually is, true. Yeah, true. So basically, it shows that I'm going to do this way. So already the verification actually showed that we there is a question from the. Okay, so there's a question from Avi. So the properties are already there. The properties are implemented underneath the design in the MCR2. And as you can see, when we have run the verification, we had two properties that being checked. We have the deadlock and the unreachable. So in the current state, the design was only able to check those two properties, and already found a problem with the code that is never going to be executed. Does it explain your questions? So the idea is that you don't have to touch the actual verification. You are only just, okay, there's a question. I think Rutger can actually answer this question. Please, if you can do that.
Essentially, the user-defined properties are the actual behavior that you describe both in your interfaces as well as in your component. So that's the extent of user properties that we support currently.
I will also add from my side that by defining the contract in the interface, it's in some way it's like unit testing the code, because we're already saying that what kind of inputs we expect and what kind of replies we expect, and every evaluation of this contract gives an error. So just like Rutger explained. Okay, so our interface is ready. We can actually implement our interface in the component, so the actual controller of the line assist. So by providing, we are saying that we want to make a port, make an instance of the interface, and this is our new instance. And for now, we basically need to copy our behavior into the component. So we also want to maintain the state of the system, but do a different action depends on the signals we are getting from the other modules. So because we already have this state in them, we want to just declare a new. We want to just inherit this in from the steering wheel and create a new line assist state, which is of course independent from the state in the interface, and just use pretty much the same guard clauses we saw here. So let's just copy that, because this is quite the same thing. And the difference is that now we need to actually refer to the specific interface. So this way and this way. Okay, is it there? Hopefully it should be there. Yeah, true. Well, there's a different way of calling the trigger from the interface. So now it should be fine, but See. Oh, I'm missing the comma. Sorry. Okay, so just let's do this step by step because, yeah, I can see it now. Okay, so the difference between the differences interface that is we need to have this parentheses, and we need to actually use the on trigger from the interface. So are you following the coding? Balance means yes. Okay, so right now we have implemented the first function from the from our requirements that we want to enable the system from the steering wheel, so we can verify the file and see how it works. Okay, so we have iSteering wheel means that we have some problems. Yeah, that's not type. There's a typo in the name. Okay. Oh my God, there's just too much problems happening. So we want to inherit. Yeah. Yeah, there is a notion that we're going to a bit too fast. So I can actually copy the code if you're not heading up too fast, and you can just use it by your own. So let me just put it on the chat. Okay, so basically that was the boring part. We actually had to introduce the same enums both to the interface and for the component. But now we can actually start to implement all the requirements we have to. So as you can see, we can do some manipulation when we are running our simulate model. We are getting all the interfaces which are yellow and the components which are green, and we can already trigger the system with the button. As you can see, by pressing, it highlights the part of the code that is responsible for the action, and we can see that all the state variables are in the interface and are in the component are changing. Okay, so far so good. So now we want to actually implement the second requirement is that we want to activate only when the minimum speed is reached. So to do that, we want to actually check the speed of the car. And to do that, we need to introduce another component, another interface, which will be called the car state. Let me just, do some information. So we are doing the interface. And this guy is going to give us a speed that we want to, well, it's going to give us the decision if we're able to enable or disable the line assist control. And typically we can use the integer values here, but to make it like less complex for the verification, we want to use the enums. So again, we have the speed, which might be below limit or above limit. And when the code will be generated, you are basically getting the placeholders for the function that will just pass you the true or false. So the easy stuff that we just, for example, evaluate is the speed lower on or higher than the configured speed is being pushed out from the actual code in the design, but will be a part of the handwritten code. And to get the speed, we want to actually create an trigger, which is called get speed, and we're going to use it by the component to check if the speed is below or above limit. Okay. Again, we need to specify the behavior. And the behavior is quite simple because we have two options. So depending on what is the speed, the trigger get speed will either reply with the below limit or the above limit. So this is the part of the design by contract approach that we need to specify all the possible things that we can get during the execution time. Okay, so now we can actually make use of this of our speed. So okay. So whenever we are in our line assist controller and the state of the system is disabled, and we are getting the line assist button, so basically the driver asks us to enable the line assist system, we need to evaluate if the speed of the car is above the limit. So basically what we do before we actually decide is it enabled, we want to ask our car state. One thing, we want to implement our interface to the component. So this time I will use a different words called requires. And basically this also makes an implementation of the interface, but it's in a bit different way. So basically, in the visual perspective, the provided interface are the interfaces that are being above the component, and required are the ones being below it. And the only difference is that the flow of the inputs. So basically, when we have our component and we have our steering wheel interface, and the interface is calling the in trigger that says, "Hey, enable the system," it goes from the steering wheel to the line assist controller. And when the interface is being required, the flow is different. This time, the component will actually use the in trigger to ask the car state, for example, to reply him with the speed limit. So because those are much more like utilities component, I'm going to use it as a required component. So my car state, we are doing our port instance. And now we can actually use the get speed trigger. So when the system is disabled and the driver asked us to enable the system, we want to call our car state interface and ask for the speed. And whenever the speed is above the limit, so again, we need to inherit from the state. So speed. So when the speed is above the limit, we want to do this following operation. So we are allowed to actually enable our system and reply with the true. Okay, let's give it a try. Okay, and already we can see that we have some problems because the interface from the steering wheel always expects to see the true, well, always expect the Boolean value. And the problem is that because we have added this if clause, when this statement is true, we will enable the system, we will reply with true, but when it's not, we are actually doing nothing. So we forgot that we actually need to do the else statement too and reply with the false. So this means that our system refused to enable that system. Okay. And now we have another problem because we said in the interface that we always expect the true button, but it seems that it's not the true. It's not an option because there might be the situation that when we will receive the on line assist button from the driver, it's not always going to end with the situation. So because we have now this speed limit, we also need to specify that it might be the case that the reply will be the false. So system refused to actually make the decision. And this is the enabled. So basically, we only need to specify it into the disabled because we want, whenever we are moving from the disabled to enabled, we want to check the true. This seems to be a little bit problematic, but it makes sure that only the relevant information is going to the system and all of them will be handled in the correct way. So just by using this design by contract approach, we are already limiting the amount of problems we can suffer from in the future. Okay, so let's verify it again. And there was a question about the properties. So as we expanded our system with more modules, you can see that we're actually doing more properties like deterministic, the deadlock, and the live lock, and also the compliance, because we are implementing the interface. So design is checking, are we actually implementing all the methods from the provided interfaces. Okay, so now we can test our requirements. So we are asking the system to enable, we are getting the speed, and now we can choose which option we can get. So if the speed is below limit, the system refuses to enable, and it just sends the false to the steering wheel. But if we try it again, I would say that the speed is above limit, the system is enabled. Okay, sounds fun. Just side note, we are pretty much close to the interactive part, where actually I will encourage you to code it by yourself. So any questions so far? And is there anyone that is not following? Goes it too fast, maybe? Okay, so I will continue. Okay, so we have another requirement which says that we will deactivate when no steering wheel contact detected for a specific time. So there are two things we need to do. First is that we need to introduce the signals from the steering wheel that will. Okay, what kind of sequence diagram? So I will just again copy maybe the code, and so you can pass it on your own. Okay. Second. Okay. Okay, let's continue. So we want to provide some signals from the steering wheel that either it has contact or not. And eventually we want to deactivate our system if there was no contact for a specific amount of time. So to start, we can actually, we need to add some triggers and events to our steering wheel interface. So the first one we're going to use is the, again, in type trigger, and it will set the driver control. But this time we don't expect any reply from the system, so it will be the void type. So we are just getting the signal, and the components will decide to do something with it, but we are not expecting any feedback for the steering wheel. And same one, which we'll call it no driver, no control. So when the driver is touching the steering wheel, we are sending this trigger. When it's actually releasing the steering wheel, we are getting this event. Okay, and because we are only interested in this kind of signals when the system is enabled, so we need to actually provide the contract for the drive control signals. So whenever we get the drive control signals, we basically we want to do nothing. Same for the drive, no control, we are doing nothing. So again, we are specifying that we can get this kind of signals only when the state is enabled. When this signal will come in the state when the system is disabled, this will mean that it's illegal. So we don't want to expect to see the signal when the system is enabled. And basically, we can actually even show this. Verify model, and we can, in isolation, we can also again check our interface. So as you can see, those signals are not allowed to be pressed, but when it's true, we are allowed to actually do the driver no control. And when the system is disabled and we are getting the signal, it means the illegal error. So design detects that even the component above us, the steering wheel, may have some bug because it's not aware that the system is enabled, and it shouldn't send us this kind of signals when the system is disabled. Okay, let's move fast to the actual implementation. So we have our signals, and we want to implement the timer for the system. So I didn't want to use it. I already have my own nice timer that works pretty fine. So now I will ask you to make a separate file called whenever you want, utilities, for example, and we're going to import this file and use it in our model. So I'm sending you the link with the code on chat, and just take your time to basically create another file, paste the code, and put it in the same folder as our main file is. Any questions at this point? Okay, so we can move up. So,
Karol.
Yes.
Yeah, if in my sequence diagram I don't get the arrows from one component to the other, or from the interface to the components.
The errors, but
the
you mean
arrows, yeah.
the arrows?
You only see the three different components. Yeah, the one from steering wheel to line assist controller, the line assist button, etc.
I actually don't know how to answer this question. So you only see the blocks, but you don't see.
Oh, this maybe you have to press the buttons below. Okay, then I see.
Okay, yeah.
I saw you acting on those. Yeah.
Yeah.
Okay.
All fine now. Okay. Okay. So when we are done with our timer, so basically this is like an external interface to the timer, which doesn't have to be instated. We can just use the timer because it has its own state. But this is just simple timer which we can set by using this trigger. We can cancel, and when the timer is active, it can inevitably send us the timeout event. By inevitable, I mean that we are breaking the contract. So we are not replying on some kind of inputs, but we just expect that at some point when the timer has elapsed, it will just send us the timeout event. So we are just listening to our timer module, and when it's being set, at some time in the future, it will just elapse and send out and will send us the timeout event. Any questions about the timer? Basically, we are just using those guys, and we don't care what is happening inside. Okay, so we want to import our timer. So what we're doing, we just need to import the file where the timer sits. So just by this, and now we are pretty much ready to go to use our timer from the utilities file. Okay, so we have our driver control and driver no control signals. So now we can actually do some timer work. Okay, so when we are in our line assist enabled, we want to actually monitor if the driver is actually holding the steering wheel. So one moment, we want to do. So we want to react on the both signals. So we have the driver control. Is it doing something? We have the on steering wheel driver no control. And eventually we have the we also need to implement our timer. So timer. Oh, sorry. And eventually, if the timer is being set, we want to do something when the timer comes. So as you can see, because we are using the timer as being required, we can actually listen to our event from the timer. So the only thing right now we are missing is from the requirement is that we want to deactivate the system when it's not being when the timer elapsed. So we need to add last event for the steering wheel, which will be called the disable line assist. So this time, because this will be the event that component will send to the steering wheel, we want to use the out type of event. Again, with the void type, because there's no logic that will handle the reply. And we can call it, for example, the disable line assist. Okay. So when the timer elapses and we want to disable the line assist controller, we want to use this event to give feedback to the driver that we have disabled the system. Of course, we need to add some handlers for the interface. So the interface is not aware of what is happening inside of the component. So just like in the timer, we need to actually make sure that it always listens to the disable and assist control. So when the system is enabled, we want to do the on inevitable, just like in the timer. And we know that at some point the disable line assist will come to us. And in that situation, we want to disable our line assist. Okay, any questions so far? This might be quite confusing, the concept of inevitable, but basically the thing is that when we are in the state enabled, we are, by saying inevitable, we are saying to interface that he needs to listen to this event that may come from the component, and there is no like contract situation like we had like this one, that we are receiving something, replying with something. Just when the system is enabled, there might be a situation that the component will just ask us to disable the system because something has happened. Okay. So now when we are done, we know that we can actually implement the logic for the situation when the driver is in control and when the driver is no control, and we have the timeout. So for the timeout, we can say that we have the steering wheel. We know that we need to send to the steering wheel the disable line assist. Okay, and now there is the part for you. So basically, we want to implement the logic for the driver control, for the driver no control. So probably we want to do some kind of timer set and timer cancel. So please go ahead and just try yourself to, for the, let's say, 5-10 minutes to implement the logic for it. Any questions about the implementation? So the idea is that when the driver has no control, we want to set the timer. When the control is regained, we want to cancel the timer, and when the timer has elapsed, we want to disable the line assist and move to the disabled state. So what I strongly recommend is to just run the verification every time you have written something, because the messages from terminal and from the sequence diagram will just guide you step by step what you are missing. And ideally, when there is no messages from the design, you should be done with the correct implementation. Okay, so let's give ourselves some like 10 minutes for the implementation. Okay, I'm pasting the code. Okay, so you can find the exact source code on the chat. please raise hand if you are done, or maybe have some questions. Okay, so any progress? Can you continue with the solution, maybe? Okay, so let's try to implement on our side. So first of all, we want to see the current state of the model. Yeah, that would be a good. Maybe someone want to share the solution. I'm interested what is the alternative path than my own, so I'll be happy to see your own solution. Okay, if not, we can try to do it another way. So when driver has no control, so let's just move it a little bit up so it looks more convenient. So whenever there is no control from the driver, we want to set our timer. And naturally, when there is a control, we want to cancel it. Okay, and as you know, when there is a timeout signal being done, we want to disable our lane assist, and also we want to change the state of the system. So we want to actually go from enabled to the disabled. Okay, makes sense. So let's try it. Okay, and we have some illegals. So as you can see, there's an interesting case of the illegal, because design shows us that the timeout signal is not being handled when specific steps are happening. So when we are trying to enable the line assist button, the speed is correct. Okay, so that the system is enabled. We have driver under control. We are setting the timer. And for some, before the timeout actually come to us, the driver pressed the line assist button to true. So the system actually moved back to the disabled state. And as we can see in the disabled state, there's no handler for our timeout. So in this situation, this doesn't mean too much because we are just not doing with the timeout anything, but in the more complex systems, this kind of interrupt exception may actually be catastrophic. So we need to make sure that whenever we are moving to the different state, we want to make sure that our timer is being cancelled. So it shows us that whenever the line assist button was pressed, we moved to the disabled state, and then the timeout actually appeared. So the simplest solution is just to make sure that our timer is being cancelled before we are moving back to the disabled. It doesn't have to be set in the state, but just in case we are canceling our timer before we move to the back to the disabled. So let's check it again. But this already shows us how much steps further design things. Okay, next we have the non-compliance. So it says that the interface promises inevitably. So this means that in this situation, and when the system is enabled, that we always should be show the inevitable. So again, the problem is that 1 second. I'm out. Oh, that's interesting. Okay. So at the end, we have promised that the interface will get at some point this inevitable, and this is happening on the enabled state. So in order to avoid this problem, we need to actually move the inevitable outside of the event, because this can also happen in different states. So just after moving the inevitable out of the scope, now it should work. Okay, so we have another non-compliance. There's a problem happening here. Let me check. Okay, so this is the live coding problems. 1 second. Okay, so we are canceling the timer when it's false, and we also need to cancel it in different case. We have a non-compliance problem. Yeah, I think we just move it to the wrong direction. So hold on a second. Okay, this timeout correct. That means this one may be a problem. Yes. Okay, we can have the same kind of problem, but I think that it was correct before. Yeah, okay. Forgot about one thing, basically, because we are using this button, so we want to make sure that the driver is able to also disable the system with the button. So when the system is enabled, the timer is not the only option that can actually disable the system. So we need to make sure that when the system is enabled, we also can observe that the system will be disabled. So where that's 1 second, I just need to figure out something. There are some problems. Okay, sorry for that, guys. Trying to work on it. Okay, I think problem is that we're missing that we always should get the inevitable, but this should be at the end point. So basically, we are promising that it will happen, but for now we just only implemented that it will happen in the enabled state. So the inevitable is also part of the braking system. So let's just move up. This should work when we actually add another option to the from the requirements. So deactivate when the braking is being applied. So for now, let's just remove it right now, because it seems that we are missing something. Okay, sorry. This is a disaster. Okay, so let's move up for now, and this should work in the in a few minutes. So we want also that the system should deactivate. We want to deactivate the system when the braking is being applied. So just to quickly introduce, we want to add the braking system interface. So to do this, we want to add the interface called the braking system. So just a short copy, we have the system that can give us the two informations. So one is the braking is being active, and this is what we are going to listen from the braking system. And whenever it comes, we want to deactivate our system. So again, just like in the example of the timer, we are just listening to the braking system, and eventually we want to disable the system. Sorry, technical break. Okay, so let's also implement our interface. And let's try to add this option. So whenever we are getting the active signal from the braking system, we want to disable our system. So just to make sure that if we're actually seeing this in the interface. Okay, so one thing. Okay, so overall, we can say that when our system is enabled, we want to also add the braking system active location. So whenever this is being true, we want to make sure that the our line assist will change to disabled again. And we are also going to set the send the disable line assist to the system, and now it should all work. So both timeout, both timeout. Okay, so let's verify the file again. Okay, so it's getting illegal because we don't. Okay, so again, the issue is that because we didn't specify when the braking system is allowed to ask to disable the system, and we are only specified that in the line assist controller that we are listening to this active signal only when the system is in enabled state. So to fix that problem, we can actually do it like much easier and just put our braking contract out of the clauses. So right now, this braking contract is valid both for the disabled and enabled states. Okay. Okay, and now it shows again that we have some problems. Again, we have pretty much complex trace for it. And this is already showing that how design is able to find all the possible problems that you can occur. So it makes sure that you're always only listening to the inputs that you actually specified in your interface. So we have pretty much complex situation. We actually enabled our system. We have set our timer, and at the same time we got the active signal from the braking system. So we have immediately moved to the disable line assist, and we have the timeout signal again. So the situation is, it might be an option that we have the timeout, and that happens just before, just after the braking system was activated. So again, whenever the system is being activated, we need to make sure that our timer is being cancelled. Because when we move back to the disable state, we don't want to get this timeout signal from the timer. Okay. Okay, and here we are, all done, I think. So when there is no errors, we can actually fully play with our model. So as you can see, we have our line assist button. We can say that we have above the limit. When driver is releasing the steering wheel, we are setting the timer. Eventually, we are getting the timeout operations, and the system automatically disables the system. We can actually do the braking system, but it's not active because the system is disabled. But even though we are still handling the signal. Okay. So as you can see, as long as there are some messages from the design, we still know that there's work to do. But at the moment when there is no complaining from the design, we are pretty much sure that this code is 100% correct, and we can just generate the code from it and use it and make sure that there will be no errors that could happen. And basically for now, that's all from my side. But just an example, I will show you like a bit more complex system that we can see. So for example, this is done like implementation of the dual clutch gearbox. So we have like a few modules. Let me show you. So we have like quite more advanced system that we can see in the saw in the workshop. So we have the mode controller, we have the gear controller, we have the valve controller. If you're not familiar, we have all those parking, reverse, drive, and neutral modes. We have the gears that we can use. So as you can see, there is plenty of code, and this is the moment when design actually starts to shine and shows you all the possible problems, because whenever you verify it, for example, it goes through all the properties we're going to check. It's getting slower because there's like much more things to check. But if you have some kind of problem, it will just show you all the steps that you need to do to get, for example, the out of range problem. So probably someone just used the code for the older gearbox and forgot to change the range from the 0.6 to 0.7. But basically, that's the whole idea, that the design is able to go through all the possible scenarios that you can see. And just to show how complex the state machine that is under the hood, we can actually generate it. So, okay, now we can see that everything looks fine, but just by the right click, we can show the state diagram of the entire system. Oh, we have some problems with the extension, sorry. Because I'm using the prototype version of the extension, but so basically it shows all the possible nodes that we can actually generate from the system and all the states and all inputs that actually corresponded to move from this state to another state. So this is all the scenarios that design is trying to verify and to see if it's correct. Moving back to our previous code, I think the good homework that I can actually ask you to do is to implement the warning break sequence if no string is contact for a longer time. So as we saw in the video, we are not actually disabling the system, but we are doing some warning sequence of the braking. So we are just doing this 3 small brake pressure. So in order to do that, we can actually create another component called the, let's say, the braking system, which would actually provide our braking system interface. Right. So basically, from now, we are not only speaking with the interface, but we also have a system that connects the braking system that connects with the line assist controller through the iBraking system interface, and we can actually ask the component to set, let's say, the emergency braking. Well, let's say warning braking. And this component will receive that trigger from the line assist controller, and when we'll do the sequence of the small warning breaks and so on. Also, we can add the component that will just do the sound warnings, etc. So this is basically the homework that you can do to implement this warning break sequence. And eventually, if there is like a longer time of inactivity, we can stop the car if there is still no response from the system. So that's basically all from my side. If there is a need and you have more questions, we can organize the follow-up meeting to evaluate the results of adding more components to the system. But basically, this is how it looks like. So, are there any questions?